Black holes are among the most perplexing and extraordinary entities in the cosmos, continuing to fascinate scientists and astrophysicists around the world. These astronomical bodies, characterized by their immense gravitational force and complete lack of emitted light, represent boundaries where established principles of physics cease to function. First envisioned by Albert Einstein in 1916 as a byproduct of his general theory of relativity, black holes were considered speculative for decades. It wasn't until significant strides in observational technology during the 20th century that their indirect detection became feasible. A major breakthrough occurred in the 1960s when astronomers investigating the Cygnus constellation stumbled upon an anomalous star, a radiant blue star radiating high-energy X-rays. This celestial body, which orbited an unseen companion, puzzled researchers until they determined it was in a gravitational bond with a colossal black hole. Named Cygnus X1, this discovery offered the first solid confirmation of black holes' existence, launching a new era of exploration into these enigmatic cosmic features. Cygnus X1, situated approximately 6,000 light-years from Earth, possesses mind-boggling properties. Its density and gravitational influence are so extreme that not even light can escape its pull, a trait that encapsulates the essence of what makes a black hole so mysterious. Since that time, researchers have uncovered many more black holes spread throughout the universe. Current projections suggest our Milky Way alone may contain over 100 million of them. Despite their elusive behavior, which complicates direct observation, astronomers have identified numerous potential black holes, ranging from those formed by the collapse of massive stars, known as stellar mass black holes, to supermassive variants found at the centers of galaxies. The impact of these objects extends well beyond their periphery, influencing the development of cosmic structures and shaping the behavior of matter in their vicinity. When an object ventures too close to a black hole, it reaches a boundary known as the event horizon. Beyond this threshold, gravitational forces dominate, subjecting the object to overwhelming tidal stresses. This violent process, referred to as spaghettification, stretches matter into elongated filaments reminiscent of strands of pasta. The gravitational gradient is so intense that it rips apart the internal structure of the object, which is then absorbed into the singularity at the black hole's core. This dramatic interaction starkly illustrates the formidable power these phenomena wield. While black holes offer unparalleled opportunities to test the boundaries of theoretical physics, they remain cloaked in mystery. Scientists continue their efforts to unlock their secrets, driven by the ambition to better comprehend the very fabric of space-time and the nature of gravity. These celestial entities, though light-years away, the nearest one being roughly 1,500 light-years distant, still provoke questions and concern due to their immense influence. In 2021, researchers achieved a historic milestone by capturing the first direct image of a black hole, specifically the one at the heart of the M87 galaxy. This unprecedented achievement offered valuable insight into the internal structure and properties of black holes. The image revealed that black holes are far from featureless voids. Rather, they possess intricate layers. Careful analysis revealed three key regions. The outermost is the event horizon, the definitive boundary beyond which escape becomes impossible. Inside that lies the photon sphere, where light is trapped in perpetual orbit due to the intense gravitational field. At the core is the singularity, a point where the known laws of physics collapse entirely, ushering researchers into realms governed by speculation and new theoretical frameworks. Black holes, though sharing this foundational three-layer model, exhibit a wide range of characteristics and behaviors, defying any simplistic classification. Consequently, traditional scientific methods often prove inadequate for their study, prompting the development of novel approaches. Since their immense gravitational fields make direct exploration impossible, indirect methods remain the primary mode of investigation. Any spacecraft attempting to enter a black hole would be crushed by the forces within, disappearing without a trace. Nevertheless, scientists persist, fueled by curiosity and determination to unlock the truth behind these cosmic leviathans. Various hypotheses attempt to explain the genesis and behavior of black holes, including those related to stellar evolution and cosmological processes. Notably, NASA's observation of M87's core delivered compelling support for the presence of a supermassive black hole influencing vast areas of space. Despite the considerable difficulties posed by their study, the scientific community continues, undeterred, pursuing deeper knowledge with vigor and hope. The study of black holes is more than an academic challenge. It's a journey to understand the essence of existence. Roy Kerr's revolutionary work in 1963 introduced a groundbreaking concept by proposing a model for rotating black holes which contradicted many earlier assumptions. Central to this model was the ergosphere, a peculiar zone around a spinning black hole where space itself is dragged along by rotation, balancing out gravitational collapse and preventing additional inward fall. This region presented unusual behavior, suggesting deeper mysteries at play. Perhaps the most fascinating idea to emerge from Kerr's theory was the possibility of an Einstein-Rosen bridge, more commonly known as a wormhole. A wormhole, according to general relativity, might serve as a bridge through space-time, potentially linking distant regions or even alternate universes. This concept arises from the understanding of the universe as a four-dimensional space-time fabric, which bends and curves around massive objects. Wormholes are envisioned as tunnels through this curved fabric, offering hypothetical shortcuts across great distances. Yet the practicality of wormholes remains highly uncertain. Theoretical barriers such as instability, quantum interference, and intense radiation render their existence and use speculative at best. Though tantalizing, the notion of faster-than-light travel via wormholes runs into significant problems. Einstein's own theories imply speed limits that wormholes may not bypass. Nevertheless, the allure of such cosmic gateways continues to inspire researchers, inviting dreams of traversing galaxies and discovering parallel worlds. Wormholes, in their theoretical elegance, symbolize the unexplored potentials of the universe and the unending human quest to reach beyond known frontiers. The pursuit of a unified theory that marries gravity with quantum mechanics, a so-called theory of everything, has become one of modern science's greatest ambitions. At the forefront of this movement stands the celebrated physicist Mayoku, whose pioneering efforts have helped shape the development of superstring theory. This theory departs from the idea of point-like particles, instead proposing that everything in the universe is composed of one-dimensional vibrating strings. Each particle corresponds to a unique vibration mode, much like musical notes on a violin string. According to superstring theory, the cosmos can be likened to a symphony of resonating energy patterns. Importantly, the theory offers potential explanations for the bizarre and puzzling features of black holes, wormholes, and other anomalies predicted by Einstein's equations. However, the framework introduces new challenges by requiring the existence of additional dimensions, far beyond the familiar three spatial and one temporal dimension. These extra dimensions, folded tightly in upon themselves, elude direct observation but are believed to shape the structure of our universe. Analogies, such as fish navigating a two-dimensional lake, help illustrate how higher dimensions might exist, unnoticed. Though imperceptible at human scales, these dimensions may influence the fundamental properties of matter and energy. The mathematics behind superstring theory has also reignited interest in the relationship between physics and geometry, revealing intricate links between numerical patterns and physical phenomena. While still theoretical, the implications of superstring theory are profound. Despite its sophistication, superstring theory remains experimentally unverified, primarily because of the hidden nature of extra dimensions. As a result, it currently resides within the domain of abstract mathematics and theoretical speculation. Yet its conceptual richness continues to attract thinkers from multiple disciplines, challenging them to rethink the universe's architecture and opening up entirely new realms of inquiry. In confronting the enigma of quantum black holes, physicists have faced a challenge that strikes at the very core of modern science. For years, attempts to reconcile quantum mechanics with gravity have fallen short. Edward Witten, a prominent voice in the field, once referred to superstring theory as a 21st century idea that landed in the 20th century. Recently, however, some progress has emerged. Independent research groups have demonstrated that string theory might solve certain black hole puzzles, at least in simplified two-dimensional models, as opposed to the full 10-dimensional version. While this marks a meaningful step forward, the ultimate answer remains elusive. The journey toward a fully unified theory continues, drawing scientists deeper into the mysterious interplay between reality and abstraction. Black holes, with their immense power and complexity, offer vital clues to the nature of the cosmos, but they also underscore the limits of human understanding.